Welcome back to vectors. All right, so 6.2. We're going to cover the last few examples from the notes. So the dot product of two vectors is what we're learning about in 6.2. We remember the definition, which we can see here, right? In class, we looked at different properties. We used the law of cosines to derive these important formula, right? U dot V is the magnitude of U times the magnitude of V times cosine of the angle in between them. You can solve this for the angle. We looked at vector projection, right? Example 7 is a really good start example. Know how to do that. And then in class today, we looked at forces and problems that involved force and work. So example 9, finding the effective force in pounds. Example 10, we worked through how much work do we find. So again, work is force dot distance. It's the dot product of your force vector and your distance or direction vector. And you've got two forms you can use. In the metric system, they use joules, which is a Newton meter. In class today, we worked through example 11, and that's where we ended. So just to review example 11, determine the work done by force F with magnitude 30 pounds acting in the direction of 3,6. So again, here's my force. It's got a magnitude of 30 pounds. It's acting in the direction of 3,6. I also recognize that's the same thing as, or it's the same direction rather, as the vector 1, 2, right? So how do we find the component form of F? If we know its magnitude and we know it's in the same direction as a vector, we want to find a unit vector in that direction. So a unit vector in the direction of 1, 2 is 1 over the magnitude of that vector times that vector. So the magnitude of 1, 2 was the square root of 5. So 1 over the square root of 5 times 1, 2 is a unit vector in the direction that I want. So F, having magnitude 30, is going to be 30 times 1 over the square root of 5, 1, 2. That gave us the component form right here. F is 6 square root of 5, comma 12 square root of 5. That's the component form of our force F. And so then AB was from the origin to 0 to 8, 0. So I'm moving this way, right? There's A, here's B. So AB is just 8, 0. And so to finish off this problem, we just took the dot product. And the dot product worked out pretty nicely because there was a 0 there. We can just say it's 48 times the square root of 5 foot-pounds, or approximately 107.3 foot-pounds. So big star next to that example. Another example that I'd like to star, which is why we are doing this video, is example 12. So let's work through example 12 together because it's almost like just one more step above example 11. So starting with, determine the work done. Okay, so over here, I know I'm going to need to end with work is equal to my force dot AB. All right, determine the work done by a force F with magnitude 60 pounds. Okay, so I know that the magnitude of F is going to be 60, and it acts in the direction of 4, 3. Okay, so direction of 4, 3. So how do I find the components of F? F is going to equal 60 times a unit vector in the direction of 4, 3. So what would a unit vector in direction of 4, 3? Well, what is the magnitude of 4, 3? Do we even need to do the Pythagorean, right? 3, 4, 5, that magnitude is going to be 5. So it's 1/5 times 4, 3. So my force vector in component form, 1/5 of 60 is 12, 4, 3. So my force vector is 48, 36. So when I take my dot product, I'm going to be doing 48, 36 dot. And now what's new or challenging about this problem is how do we find AB? So looking at here, in moving an object 4 feet. So actually, we're going to change the units just so we get practice with those joules and newtons and meters. So if instead of 60 pounds. What if I said 60 newtons, N? Okay. Does anything change in how I find the components? No. And if instead of moving 4 feet, what if I change the units to be meters? M for meters. Or just write out the word meters. Does anything change in what I'm about to do? No. Just the end results, right? My work, a Newton meter, is a joule. So at the end, those will be my units. All right, looking at and moving an object 4 meters. Okay, so that's giving me the magnitude of AB. I want to move it 4 meters. From 0, 0, so that's point A. So here's 0, 0, A. To a point in the first quadrant along the line y equals 2x. Okay, so the line y equals 2x, I know that has a rise of 2 and a run of 1. So it's going to look like this. That's my line. Y equals 2x. I don't know where point B is, though. So I'm going to arbitrarily put it here because what do I know? I know the distance from A to B is 4. So I know this distance here is 4. And so if that distance is 4, B, what can I say about this ordered pair? Right now I could just say, well, it's x comma y. It's unknown coordinates. But is it really unknown if I know that the hypotenuse here should be 4? And do I know how x and y are related? I do. Right? Y is 2x. So really, this is the ordered pair x comma 2x. So what is AB in vector form, right? That's B minus A in terms of the coordinates. So I've got x minus 0, 0. So x minus 0 is x. 2x minus 0 is 2x. Okay, so I know the magnitude of AB is 4, right? I know the component of AB is x comma 2x. So what is that magnitude, right? What is the magnitude of AB if I know that the component form is x comma 2x? Well, that magnitude is going to be the square root of x squared plus quantity 2x squared. But that's got to equal 4. All right, so then solving this, what can I say? If I square both sides, that means x squared plus 2x squared is 4x squared is going to equal 16. So 5x squared is 16, which means x squared is 16 fifths, which means x is going to equal 4 over the square root of 5. And how do I know that it's positive and not plus or minus? Because it tells me I'm in first quadrant, so I'm going positive. So B is positive, positive. So if that's x, well then that means 2x must be twice that. So 8 times the square root of 5. So AB now in component form is 4 over the square root of 5, comma 8 over the square root of 5. So that is what I'm going to take the dot product with. So 4 over the square root of 5, comma 8 over the square root of 5. And let me move my video over here for a moment. And let's do this multiplication. All right, so what have we got? We've got 48 times 4, 48 times 4, all over the square root of 5, plus 36 times 8, all over the square root of 5. So I've got a common denominator of the square root of 5, at least. That's going to give me what? When you multiply this and add it out, it'll save us a little time. It's 480 all over the square root of 5. All right, so if I rationalize my denominator, because 480 is easily divisible by 5, right, this is going to simplify to being 96 times the square root of 5. And so, what's my work? My work exactly is 96 times the square root of 5 joules, or approximately, when you punch that into your calculator, 214.66 joules, because I switched my units from pounds and feet to newtons and meters, and a newton meter is a joule. All right, so look at that problem, pause the video, rework it yourself if you need to, but that's a really good example. Then there's just a few more examples in the notes. If we look at example 13, this is very similar to homework problem number 41 in your textbook. So let's work it out. Consider the line L with equation 5y minus 2x equals 10. Determine its x and y intercepts. All right, that's easy. So A, It's x and y intercepts. So its x-intercept is when y equals 0. So when y equals 0, that means I've got 0 minus 2x equals 10. That means x should equal -5. So its x-intercept is the ordered pair -5, 0. And we're going to call that point A. So that's A. And then its y-intercept. All right, so its y-intercept. That's when x equals 0. So that would mean 5y minus 0 is 10, and so that means y has to equal 2. So that is going to be the ordered pair 0, 2, and that's B. So I could graph that. 1, 2, 3, 4, 5. There's point A. 1, 2. There's B. My line has a positive slope of 2/5. Right, so this is line L. That's point A. This is point B. Find the coordinates of the point P so that AP is a unit vector, so I want the magnitude of AP to be 1, and is perpendicular to L. Okay, so if this is my line L, and I want AP, so perpendicular is going to look something like this, but I want it to be a unit vector, so I want P to be somewhere like right here, so that distance there is 1. And I want, or technically I'm going to have two options. I could be above or below. So we'll call that point 1 and point 2, where I want that there. So how do I find the coordinates of these points? I can easily draw it and kind of visualize it, but how do I find those coordinates? Well, again, we're going to take this, the slope of my line here is, what did we say? Rise 2, run 5? 2/5. So what would the slope of the perpendicular guys be? Right? The slope of our perpendicular would be -5/2, or 5 over -2. So what you are thinking about, we can think about the fact that I can have vector, right? So vector, if I rise 5 and go backwards 2, right? So that would be 2, -5. Horizontally, I would be going 2, and then I'd be going down 5. Or I could be -2, 5. I could be going backwards 2 and up 5. Those vectors are perpendicular. They're orthogonal to vector AB, which is 2, 5, right? That would be my AB, right? A, B, going from A to B. I would have 0 minus -5 is 5. Sorry, not 2, 5, 5, 2. And 2 minus 0 is 2. So 5, 2. Again, how do I know that they're perpendicular? You can look at the dot product. If I took the dot product of this with either of these, I'd get 10 minus 10, or minus 10 plus 10 adds up to 0. So with those vectors, I need them to be unit vectors now. Okay, so what is the magnitude of 2, -5? Or the magnitude of -2, 5? The magnitudes are going to be the same. Those vectors have magnitude. 4 plus 25 is the square root of 29. So a unit vector, right? So I need AP1, say. AP1 would be, well, my x would be going backwards, that'd be this negative, so -2 over the square root of 29, 5, the square root of 29. Let's move this over here. And then AP2 would be right here. I'm going positively, so that would be 2 over the square root of 29 and -5 over the square root of 29. So as decimals, those are roughly -0.37, 0.93, so 0.37, -0.93. So those are the vectors. So what is the coordinate of point P itself then? Point P itself, right, P1, instead of being over here at -5, it is now -5 and 3/7, wow, -5 and 37 hundredths. So -5.37, and it's up 0.93. P2